So by now you're probably recognizing that as we add more and more carbons, there become more and more isomers. And one of the questions that's often asked is, draw all of the constitutional isomers of a particular alkane. So I'm going to give you some guidelines in terms of how you'd actually go about doing this. So the first thing that you need to do is start by simply drawing the longest unbranched carbon chain, and this gives you one particular constitutional isomer. Then what you're going to do is you're going to shorten that carbon chain by one carbon, and that leaves you with a methyl group that you can add to all of the positions on that carbon chain that's now shortened by one carbon. And you have to make sure that they yield new isomers. This can be tricky, so be careful in how you actually go about doing so. Make sure that you are actually creating a new isomer. One way of doing this is simply by naming them. If a compound has a different name than another one, then you know that they are isomers of one another. And then, of course, once you do that, you're going to shorten the chain now by two carbons. And when you shorten the chain by two carbons, you have either two methyl groups that you can add, or you have an ethyl group that you can add to the existing carbon chain. Again, you have to be careful to make sure that you're not lengthening the carbon chain by adding a particular substituent. And you continue to do this until you can't get any more isomers, right? That's basically the short, abbreviated, way of making sure that you get all of the isomers of a particular alkane or alkyl derivative. So let's look at an example, and let's do something that's a little bit challenging to do, and we're going to try to draw all the isomers of C8H18. So the first one should be relatively easy. It's octane, right? All 8 carbons are in one chain. The next step, remember, is to remove one of the carbons. So remove the carbon at the end of the chain, you get now a 7 carbon chain, and you're left with a methyl group that you have to basically place on that 7 carbon chain. Notice I can't add methyl group ever to the end, because if I added it to the end, it would simply be extending the longest continuous carbon chain to now 8. I would get octane. But I can add it to the second carbon, and I get 2-methyl heptane. I can add it to the third carbon and get 3-methyl heptane, or I could add it to the fourth carbon and get 4-methyl heptane. Notice at this stage, if I go any further to the fifth carbon, I can number it in the opposite direction, and it's actually 3-methyl heptane. So when I have one methyl group adding to this chain, that's pretty much where I end. So I go to the next step. I remove 2 carbons from that 8 carbon chain. So now I have hexane, and I'm left with either 2 methyls or an ethyl. So let's see how we can add 2 methyls to this particular structure. Well, the first thing is I can add the 2 methyls both to the second carbon. Now, the next step is that I can then go from essentially keeping one carbon on the second carbon and moving the second carbon down the chain. So I get, in the first one that was 2,2-dimethyl-hexane, now I get 2,3-dimethyl-hexane. Then I get 2,4-dimethyl-hexane. And lastly, I get 2,5-dimethyl-hexane. Again, I can't go any further because then I would be extending the longest continuous carbon chain to heptane now, and I already have 2-methylheptane. Now, is that the only way that I can add 2 methyl groups? Well, certainly not. I could actually add both of the methyl groups onto the third carbon, and that gives me 3,3-dimethylhexane. And I can do something similar in that I can leave one of the methyl groups on the third carbon, move the second methyl group onto the fourth carbon, I get 3,4-dimethyl hexane. So notice 2,2, 2,3, 2,4, 2,5, 3,3, and 3,4-dimethyl hexane. That's a lot of derivatives of hexane. Are we done? No, we're not, because we not only can have a methyl group, two methyl groups, we can also have an ethyl group. When you add an ethyl group, you can't add an ethyl group to the end, just like you can't add a methyl group. You also can't add an ethyl group to the second carbon because you would be increasing the carbon chain. But you can add an ethyl group to the third carbon. And so this is the only derivative of hexane that I can have with an ethyl substituent. So notice the larger the substituent gets, the less possibility you have of actually using it because it tends to increase the carbon chain and you don't get a new isomer. The next step is to shorten it again to now 5 carbons. Now I have a 5-carbon chain of pentane, and I can have 3 methyl groups. I can have a methyl and an ethyl, or possibly a propyl group. We're going to see that propyl group can't actually exist on this because if I add a propyl group to anywhere on that 5-carbon chain, it's going to lengthen it to 6 carbons. At the least, right? So I start with my 3 methyl groups. I can add 1 carbon on the second, 1 methyl group on the second carbon, 1 on the third, and 1 on the fourth. So I get 2,3,4-dimethylpentane. I can have 2 methyl groups on the second carbon and 1 methyl group on the third, 2,2,3-trimethylpentane, or I can have 2 methyl groups on the second and 1 on the fourth, 2,2,4-trimethylpentane. And lastly, I can have the 2 methyl groups on the third carbon and the third methyl group on the, you might think fourth, but it actually becomes second, so they're symmetrical there, and so I get 2,3,3-trimethylpentane. Now, lastly, I can use an ethyl and a methyl group. Ethyl, there's only one way to make an ethyl group or place an ethyl group, and it's going to be on that third carbon. So the methyl group could be on the second carbon, or the methyl group could be on the third carbon. And lastly, I can decrease the carbon chain to 4 carbons. And now really the only thing that I can add are methyl groups, and I have 4 methyl groups. How do I add them? There's only one way. 2 methyl groups on the second carbon, 2 methyl groups on the third. I get 2,2,3,3-tetramethylbutane. And we see that there are 18 total isomers in drawings of C8H18. That's a lot of isomers. And guess what? C9H20, even more. And it continues on and on.